Hi, ChatGPT. I asked it, let's do a thought experiment. It said, sure, what kind of thought experiment would you like to explore? I says, we're in a void with no gravity, in a sealed box. We have no direction, no weight. The box has water at the bottom and air at the top. Even if we then push it or accelerate the box up relative to your feet, then we get weight and direction, correct? We also get a pressure gradient of the air above the water. Yes, that's correct. Here's what happens in that scenario. Initial situation. You're in a sealed box floating in a gravity-free void. Water is at the bottom, only because the box was arranged that way, but in 0G the water and air would normally mix or form blobs unless held by a container structure. Inside the box there is air on top and water on the bottom. Perhaps it's held by internal tanks or by surface tension. You might about that. I mean, it might have been floating around before, and as soon as it starts accelerating, it settles into the state. So in this state, no weight is felt, no preferred direction exists inside the box. You accelerate the box upward. If an external force starts pushing the box upward relative to your feet, i.e. the floor of the box accelerates towards you, the box floor accelerates into you. You feel a reaction force from the floor. This reaction force is indistinguishable from gravity. This is the equivalence principle. Thus you now feel weight, with down being the direction opposite the acceleration. What happens to the air and water? Air and water respond to acceleration just like they do to gravity, because a constant acceleration is equivalent to a gravitational field. So air develops a pressure gradient, high pressure down towards the accelerating wall, the floor, and lower pressure up, just like air in Earth's atmosphere under gravity. Water also develops a hydrostatic pressure gradient. Its surface becomes flat and perpendicular to the direction of effective gravity. The water stays at the bottom against the upward accelerating floor. Interface between air and water. The boundary between water and air behaves exactly as if you were in a gravitational field. You now have stable stratification, water at the bottom, air on top. Summary. Yes, by accelerating the box, you create an artificial gravity field. You produce a consistent up-down direction. You create pressure gradients in the fluids, the water and the air. Everything behaves as though gravity were present. This is a direct manifestation of Einstein's equivalence principle. Constant acceleration is physically indistinguishable from gravity. And it says, if you want, we can say, I says, no. So the fact of the matter is that in this scenario, we would get the same as if we were on the Earth in a gravitational field, yes? Yes. As long as the box accelerates at a constant rate, everything inside behaves exactly the same as if it were sitting in a gravitational field of the same strength. This is not approximately true. It is exactly true in all ways that can be locally measured. You would observe weight. Your body would press on the floor with a force proportional to the acceleration A, just like gravity G. A pressure gradient in the air. Air pressure increases with depth, exactly as on Earth. Water behaves like it's under gravity. The water settles at the bottom, the accelerating wall, its floor, and forms a flat surface. Objects fall. If you drop something, it accelerates downward at the same rate as the box's acceleration. Buoyancy works. Bubbles rise in the water, lighter objects float, etc. Your inner ear senses gravity. Your vestibular system would say you are standing in a gravitational field. Why is this true? This is exactly Einstein's equivalence principle. A uniform gravitational field is locally indistinguishable from a uniformly accelerating frame. The only difference between Earth gravity and constant acceleration come from tidal effects and curvature. But we've looked for curvature, we can't find it, so we know there's no curvature. But inside the small box, you can't detect them. So for all practical local measurements, your accelerating box equals gravity. If you'd like, we can extend this to rotation, varying accelerations, free fall, or relativistic effects. I said, explain a uniformly accelerating frame. What is it? A uniformly accelerating frame is simply a viewpoint, a reference frame that is accelerating at a constant rate in one direction. Let's break that into something intuitive. What is a frame? A reference frame is just the point of view you use to describe motion. A train is a frame, a room is a frame, a spaceship is a frame. Inside a frame, you describe where things are relative to you. What makes a frame uniformly accelerating? A frame is uniformly accelerating if its velocity increases at a constant rate. Example, a spaceship that is firing its engines so that its speed increases by 1 meter per second every second in a fixed direction. That's a constant acceleration inside the spaceship. The floor pushes up on you, you feel weight, down is the direction opposite the acceleration. This accelerating spaceship is a uniformly accelerating frame. Why is this important? Einstein noticed something profound. The physics inside a uniformly accelerating frame looks exactly like the physics inside a gravitational field. A constant acceleration of 1g feels the same as gravity. The air pressure changes with height the same way. Water lies flat. Objects fall. Clocks tick the same way gravitationally. This is the equivalence principle. One important detail. A uniformly accelerating frame means acceleration is constant in time. Acceleration is the same everywhere in the small region you're looking at. If acceleration changes with time or position, it's not uniform, and the behaviour no longer perfectly mimics gravity. In a sentence, a uniformly accelerating frame is a moving reference frame whose acceleration is constant and unchanging, producing effects identical to those of a constant gravitational field. If you want, we can explain this, and this, and how it answers. Does the frame have to get faster and faster, or could it stay the same as 1g? Great question. This gets to the heart of what 1g really means. To feel 1g, the frame must keep accelerating. If a spaceship wants to simulate gravity, it must continue accelerating at 1g. That acceleration automatically means the ship's speed increases more and more over time. There is no way to feel 1g without constant velocity. Constant velocity means no acceleration and therefore no artificial gravity. Why the frame must keep getting faster? To create a force on you that feels like weight, the floor must push on you. It does this only when it's accelerating into you. Floor pushes upward, you feel weight downward. Stop the upward acceleration, floor stops pushing, you go weightless. So the only way to feel a constant 1g is to keep increasing velocity at 9.8 meters per second squared. What if velocity stays constant? If the ship just moves at a steady speed of, say, 10,000 meters per second, but not accelerating inside, no force pushing on you, you float, no pressure gradient, no down direction. Because constant velocity equals zero acceleration equals zero artificial gravity. Does this mean speed grows forever? From the ship's own perspective, it can accelerate at 1g forever. From an outside observer's perspective, relativity, you approach light speed but never catch it. Your acceleration appears to soften as you get relativistic. But inside the ship, you always feel 1g, as long as the engines keep providing 1g of proper acceleration. This is used in interstellar travel concepts. A ship accelerating at 1g, halfway, then decelerating at 1g, can cross vast distances while keeping humans comfortable. Short version. Feeling 1g requires constant acceleration. Constant acceleration means your speed keeps increasing. Constant velocity cannot produce artificial gravity. Excuse me. So once you get to a certain speed, you can no longer get faster. But does that mean that you continue to feel 1g in the reference frame? Yes, you continue to feel 1g in your own reference frame, even when your speed gets so high that you cannot get faster in the normal sense. This is one of the most unintuitive but important ideas in relativity. Let's break it down clearly. Inside the accelerating frame, your spaceship or the Earth, you keep feeling 1g. As long as your engines, or whatever's pushing the Earth, continue to provide 1g of proper acceleration, you will feel weight equal to Earth's gravity, a clear down direction, air and water behaving normally under gravity, normal walking, normal pressure gradient. This is true no matter how fast you are going relative to anything outside. Why you still feel 1g even at near light speed? Your speed relative to external observers approaches the speed of light, but your proper acceleration, the acceleration you personally feel, stays constant. This happens because relativity changes how outside observers see your motion from your perspective inside the ship. The engine pushes with the same force. You feel the same 1g. Your time slows relative to outside. You never notice anything preventing acceleration. From the outside observer's perspective, you get closer and closer to the speed of light. Your acceleration appears to weaken. You never reach c, but you can get extremely close. Because time dilates for you, you can still burn the same amount of fuel per ship second and feel constant thrust. Analogy, your speed limit changes. Imagine running on a treadmill that speeds up under your feet. You normally run at 10 miles per hour. But if the treadmill moves under you faster than you can run, relative to the machine at the same effort. Even if the ground says you're going 100 miles an hour, you'll feel like you're jogging at 10 miles an hour. In relativity, space-time itself is doing the treadmill effect, letting the ship continue to feel the same push even though its external velocity is hitting relativistic speed limits. Key idea, you don't need to go faster to keep feeling 1g. You only need the engines to keep providing 1g of acceleration in your own frame. Relativity does the math. that makes both statements true. You never exceed the speed of light externally, you feel constant gravity internally. Excuse me. Do you still feel 1g when you can no longer increase your speed in the Newtonian sense? Yes, absolutely. Because you feel proper acceleration, not coordinate acceleration. Proper acceleration can remain constant even when speed asymptotically approaches c. If you want, I can show blah blah blah. No, I said what would happen if you dropped an object? If you're in a spaceship or box, well, let's just say the Earth, accelerating it at 1g, and you drop an object, then it behaves exactly as if you dropped it on Earth. Even if the ship is going 99% the speed of light relative to the outside universe, inside the ship the physics is ordinary and simple. What you see when you drop the object. You let go of the object, the floor is accelerating upward at 1g. The object is not being pushed anymore because it's not attached to the Earth. Right? Not attached to you because it's not attached to the Earth no more, or the spaceship no more, the floor of the ship. Right. So the floor rises to meet it. To you inside the accelerating frame, the object falls downward with acceleration of 1g. It's the floor just like on Earth. This is why this happens. This is because what you feel as gravity in the ship is actually proper acceleration. The ship is accelerating around you, but the dropped object is not. You are forced upward by the floor. The object is not. So you and the object separate exactly as they would in a gravitational field. This is a perfect demonstration of the equivalence principle. A uniformly accelerating frame is locally indistinguishable from a gravitational field. From the ship's reference frame, it looks like the object accelerates downward at 9.8 meters per second squared. Your gravity is perfectly normal. Water has a flat top, air has a pressure gradient. Everything behaves Earth-like. From an outside observer's reference frame, things look different, but still consistent with relativity. The ship accelerates upward, the dropped object continues in a straight line at constant velocity, free motion. The ship's floor moves up to meet it. But inside the ship, none of this is noticeable. The physics is identical to gravity. In short, inside a 1g accelerating spaceship, a dropped object falls just as on Earth. You see it accelerate downward at 1g. The appearance of gravity is exactly reproduced. That's it. So, the Earth, it's accelerating, but only at 1g. So you constantly feel 1g no matter how fast you get and how fast it gets. And then you can only get to a certain speed and it can't go any faster. And you will still feel that 1g. So basically, you cannot distinguish between if the Earth is moving up and like the spaceship, or things are being pulled down to the ground. And in my honest opinion, it's the Earth that's moving up to meet the object. It's the accelerating reference frame, which it would be exactly the same as what we experience here on Earth. Exactly. So that's it. So thank you for watching, and I hope you have a good weekend.